All right, good evening. So I'd like to start out by asking, how many of you are going to be at the conference? So maybe more than half. Most of you are going to be at the conference. Well, that's great. I look forward to seeing you all there. What I'm going to start with is a lightning talk that I gave at ACCU last week, and it went really well, so I thought I would share it again, and then we'll do kind of the advertised talk will be after that. How many of you are familiar with the idea of a lightning talk? You know what a lightning talk is? Yeah. So we're given 5 minutes to do the talk, and so we tend to talk really fast and say things really quickly. But this talk is called "Why We Can't Have Nice Things," and it's about East Const, and the name East Const actually comes from Simon Brand. It was a tweet that he did late last year, and he said, tag yourself. Are you East Const or West Const, depending on how you write const relative to what you're declaring to be const. This is a very old idea. Simon just came up with a new name for it, but the concept has been around for a very long time. Dan Sachs was writing about this in the mid-90s. Sometimes it's called consistent const. And the idea is that in C and C++, const applies to what's on its left, unless there is nothing on its left, and then it applies to what's on its right. So if you look at my code, because my code I follow what I call the consistent const rule, I have a different rule. My rule is const applies to what's on its left. Full stop, right? But I have people sometimes say, wait a minute, don't you want to be, when you're declaring, for example, an integer const, don't you want to read it as a constant integer? Because I speak English. In English, adjectives come before nouns, right? So that just makes sense. You say a constant integer. And I say, yeah, absolutely. It's exactly what I want to say. But the assumption that you're making is that you're going to read this from left to right, which is how we normally read language, but that's not the correct way to read a declaration. In C and C++, declarations are actually read inside out and right to left. Now, what do I mean by that? Well, what is this declaring? Right? This is declaring fn to be a pointer to a function that takes an int and returns a void, right? Inside, out, and then right to left. And in this case, what we have is ra is a reference to an array of 3 longs. Again, inside out and right to left. In this case, it's just a simple pointer, so PC is a constant pointer to a character. And then it makes sense then when you would say PC is a constant pointer to a constant character. The constant is on the right of what it declares, and it's the correct way to read it if you understand how to read declarations correctly. In this case, RI is a reference to a constant integer. Okay? All right. And now there are some things in the language where you must be East const. If you're declaring a pointer, as we just talked about, the const must be to the right of what it declares. And if you have a member function, then const again has to be to the right of what is const. Now, if you follow this rule, it clears up some things that can be confusing to people who are used to doing the more traditional kinds of constness, which some people call West const or preference const. But in this case, again, to some people who've never looked at East const, this could be confusing because they don't know it. Well, is the char const or is the pointer const? It's just as far to both. And in this example, if you have an alias for a pointer to a widget pointer, and then you put const in front of it, again, someone who uses preface const might be confused and might think, well, wait a minute, this is a pointer to a const widget. Of course, people who are smart, attend user groups, stay on top, you're not going to be confused, but other people might be, right? This, of course, is how you'd write it in East const, and it makes it much clearer that what is const is actually the pointer, not the widget. So I actually wrote this blog because one of the things that irritates me is sometimes when I think about how to write code and I say, hey, here's a better way to write code, and I propose this, the argument I get back is, well, we can't use that, we can't do that, because we have several million lines of existing code that don't work that way, and so we can't use your system unless we could change all this code overnight. And the problem I had with that is that it's very narrow-minded. It's as if you're basically saying, we're locked into something we're never going to improve, right? We have to be consistent, so we're never going to improve. And this is the argument that's essentially happening. This is from the core guidelines. And in the core guidelines, they're basically saying, I'm not going to read the whole thing, but it's basically saying, don't use East const. Use the more traditional. And they even say, it's actually more logical, but but we don't want you to do it. And the reason we don't want you to do it, that we're hiding behind novices. We're saying, well, beginners may not understand it, and so we don't want you to do it. And the reason is because there's so much training material that does the old way. So instead of fixing our training material, we're going to condemn the entire industry to a less logical approach, right? I notice also it says in enforcement, it says, we're going to flag const whenever it's used as a suffix. And yet, look at the example here, even the good example. Const is used as a suffix, which it has to be because it's a pointer. We're going to flag this? This is crazy. That's why we can't have nice things. The message here is, if you must remain consistent with the past, you can never improve. You've locked yourself in. And that's what I'm objecting to. So I don't know if I've encouraged you to use East Const or not, but I hope I've encouraged you to be open-minded about these kinds of things. And of course, I am encouraging you to join the revolution here and even sign the petition where we're asking for a petition for const conservancy. I actually have wristbands for you at the end. Yes?
You did not mention one reason which I consider. You did not mention one reason to use East Const, which I consider significant, is for those people who prefer nice vertical alignment and no gaps of white space. East Const is perfect for this. West Const is not. Is not.
Yes. All right, thank you for that. As I said, if you're interested in a wristband, I've got some here. I'm happy to distribute those after the talk tonight. So that's the end of the lightning talk. I'm now going to switch over and give the talk that we were promised tonight. And it's called Modernizing Effective C++. So how many of you know who Scott Myers is? Everybody heard of Scott Myers? Everybody know all about Scott Myers? That's great to see. That's wonderful to see. So Scott wrote a series of books on effective C++, effective modern C++, effective STL, effective C++, more effective C++. He wrote all these books. However, the first three of these books were written for classic C++. Not this one, but these three were all written for classic C++. So this is kind of a problem. Do we want to recommend these books? There's lots and lots of really, really valuable information in these books. These books contain information that every C++ programmer should know, even if they're doing modern C++. But the problem is they kind of need to be updated. You wouldn't want to blanketly recommend these, because if you absolutely follow it exactly as it's saying, you're missing out on opportunities for improvements. And so they really need to be updated, and the problem is it's not obvious how to update. You really have to understand what he's recommending and understand modern C++ in order to figure out what should the real recommendation be today. But that's what I do. I do training, and so I've licensed Scott's classes, and I've gone through the process of updating the recommendations. Now, in many cases, the updates are kind of obvious, straightforward. People who are experienced and understand what Scott was writing about, understand modern C++, they can figure the updates out. But sometimes there's surprises, and so that's what I'm going to present tonight, is what I think is kind of an interesting and surprising update for C++. So let's start out with one that I think is just wrong. And again, I want to emphasize that almost everything Scott says is very, very valuable. It needs to be updated, but it's the guideline you want to follow, but this is an exception. One of his guidelines is he says, use the literal zero, not the macro null for null pointers. This is true. We don't want to use the macro null for null pointers, right? Everybody's on board with that, but this is not good advice. What's the good advice?
Null pointer.
Null pointer. Okay, so this is better advice. All right, we all get the idea? This one's easy. I got something a little bit more interesting. All right, so my question is this going to compile? Will this compile? I have three integers, a, b, and c, and I add a and b, and I assign c to that. Is that going to compile? It should not. Okay, no. Compiler is not going to allow us to modify temporaries as R values of fundamental types. Does everybody see why? Let's think about what this is actually saying to do. This is a sub-expression, a plus b. If I have a large expression and I implement any part of it, even if I'm just adding three numbers, can the compiler add three numbers? No. It has to add two, and then add one to the result. That's the way the compiler works. It only adds two numbers at a time. So even if I have an expression as simple as adding three numbers, there's an intermediate expression. So what does the compiler do with the intermediate expression? It creates a temporary out of it, an R value. And what does it do with R values? Well, the standard doesn't tell us, but what do we know? It's going to put on the stack, right? So that's what's happening here, is A plus B added together, put on the stack, and then we're assigning C to the answer. Does that logically make sense about what we've asked it to do? You're shaking your head because you think that you misunderstood my question. I'm not saying, do we want it to do that? Or would it do that? I'm saying, does what we're asking it to do, does that make sense? Where we're actually just going to calculate a result and then assign something to it. That makes sense. The compiler could generate that code. But it won't. Why will it not? Because now you're saying, no, it doesn't make sense to do that. Why? Because this is a temporary. This result's going to be thrown away. It makes absolutely no sense to assign a value to it. Don't assign a value to something, throw it away. What is that doing? It's advancing the heat death of the universe is what it's doing. It is a complete waste of time for us. It's a waste of power and a waste of cycles. We don't want to do this. And that's why the compiler is stopping us. It's not because the compiler couldn't do it. Because what we're asking it to do is something that makes sense to do, makes sense in the sense that it could do it, but doesn't make any sense that it would do it. So that's why it's not legal. All right. Now I want you to think about this class that Scott has invented for us. He calls it an unlimited percent integer. So most integers, we know it's 32 bits, 64 bits. It has some precision in the integer. But this is an unlimited precision integer. How can we do that? Well, we'd implement this the way we implement a string, right? We're going to put bits on the heap. If you need more precision, we'll allocate more space, just like a string would. Does everybody understand the class we're talking about? Okay. Now, this is a numeric class, so of course we want to do numeric operations on it. So we're going to declare operators such as the addition operator and the division operator. Everybody on board? Make sense what we're trying to accomplish? Okay. Now, here's the deal. If we were to write this, will the compiler be able to actually do this? Sure, because what it's going to do is it's going to translate it into this, right? The operators are just symbols that the compiler knows is equivalent to some kind of function, right? So it translates this into this and executes it. Everybody on board? Okay. Now, here's the deal. Now we're going to ask you, does this make sense? Does that look familiar? For the exact same reasons we just talked to a minute ago, this is something we wouldn't want the compiler to do. It is a complete loss to society, right? To create a temporary and then assign a new value to the temporary, which is then going to be thrown away. Adding these two together, the answer will be put on the stack, and now we're assigning a value to that, and then we're throwing that away. Now, a good compiler will optimize that away, but it will not flag it as illegal, because that's legal code. Why? Because it will just translate it as doing this. Now, why is it that when done with fundamental types, it's illegal and the compiler won't let us do it, but when we do it with user-defined types, the compiler allows it? Why?
There's no const. We should not catch integers.
But there wasn't const with integers either. What was my question? My question is, why was it not legal with fundamental types, but it's legal here? Why?
Because compiler just knows much more about fundamental types than about custom classes.
That's essentially correct, yes. The standard has said the compiler isn't allowed to make any assumption about what this class might be doing. Remember, these we know what it is, because we decided what it is. It's a bunch of bits on the heap. That's what it is. But it might actually represent things on disk, right? We don't know what these classes are. And these operations, the compiler's not allowed to assume that just because you're using a plus sign, there's actually addition going on. It could be concatenation. It could be anything. Right? So the compiler is not allowed to make those assumptions, and therefore this is legal code. Now, a compiler that can inline, that if alt sees this as inline, it might very well optimize it away, because it might say, well, you're doing something that clearly has no side effect. It could optimize it away. But that's where we are. But now the question is, do we want this to compile? And what Scott is suggesting is, no. If it doesn't make sense for ints, it doesn't make sense for our unlimited precision integer. So, what do we do about that? How do we prevent it from compiling? Well, so the idea is that if you make a change to a temporary, that is going to be lost at the end of the expression when the temporary is destroyed. So modifying a temporary, suspect because the changes are going to be lost, and modifying it, those modifications being lost mean they're probably a waste of time. And if you've asked for those modifications, you were probably confused about what you were asking for. So there's probably a logic error as well. So catching that would be a boon to us, correct? So what Scott has recommended in classic C++ is that we return these as const. Now let's think about what's going on here. If we return this as const, will this work? Will this top expression here, will that work? But we're returning to const. How can you assign it? Because we're reading from the const object. The A is not const, but the result of B and C is const, but we can read from a const. So declaring this as const is no problem at all. However, it stops us from doing the second one, which is what we wanted to stop. So that's why Scott makes that argument that that's what we want to do. Does that make sense? All right. Now here's the problem. So the operator returns a const, so the last line won't compile. If you wrote this, maybe what you really meant was equal instead of equal. How many of you have done that? I've definitely have done that, right? Pretty easy to do. The compiler will now catch that and say, no, you can't do that, right? You can't assign to that. All right, so it catches that. So now the question is there any time when you would want to modify a temporary?
Sure.
When would you want to modify a temporary?
String replaces.
What's that?
Chained string replaces.
Those aren't temporaries, though. Those are usually named objects. Usually.
They can be temporaries easily.
They could be. But that's a pretty rare use case. There's a much more important use case, particularly in modern C++. When you want to move from it. So Howard Hinnett, who knows who Howard Hinnett is? What Howard Hinnett do? Actually, he's done so many things, I don't want you to start listing them all. He wrote the date class most recently, but probably the thing he's most known for is he created move semantics, right? So Howard said you never want to modify a temporary except when you do. And what he meant by that is sometimes you do want to move from a temporary. And in that case, we're not really caring about what the temporary is going to eventually be because we're throwing it away, but we would like to take its resources first. And we need to modify the temporary to tell it, I've taken your resources, so don't try to clean up when you go out of scope. Does that make sense? All right, so everybody's on board. All right, so the problem now we have is thinking about what's the data in the unlimited precision class. What is it? We said what the data was. What's the data? Bits on the heap. Would we want to be able to move those? That's exactly the kind of resource that we would like to move with move semantics. Can we do that if we return const? No. So that's the problem with Scott's advice. That's why we need to update it. We want to be able to do moves, and in modern C++ we can do moves. Notice, in classic C++ we couldn't do moves. So Scott's advice to say returns be const was good advice. It prevented us from modifying temporaries, but it doesn't work in a modern context where you would like to be able to do moves. So what we might say is that we want to return const objects when you want to emulate all value semantics of fundamental types, but not if you want to enable move operations. If the type has resource that can be moved, you want to enable move operations, so we don't want a const return type. Does that make sense? So that's a modern update of what Scott had advised. Now, I want to create a Pascal array class. How many of you have used Pascal? Wow, I'm impressed. Usually it's only old fogies that have used Pascal. You guys, great. So the thing about Pascal is when you declare a Pascal array, how is that different from declaring a C++ array?
The index can be any.
That's right. You give it any index you want. In C++, you can have any beginning index you want as long as what you want is 0. But in Pascal, you really can't have whatever you want. So that's what we're going to try to do. We're going to do a Pascal array. Notice, though, if you do a C++ array, we can't assign arrays. So if we want to emulate that with our Pascal array, then we would like to be able to make this not compile. Now, in C++, it's easy to make something not compile. You just don't write it. If you don't want to print, you just don't write a print function, okay? But there's one place, actually a few places, where that doesn't work, and that is with copy assignment, right? Why? Because if you don't write the copy assignment, the compiler's going to. The compiler really thinks that you want to copy things, right? So what do? Well, we need to find a way to prevent this from compiling, and in classic C++, what we did was we declared it to be private. Now, that meant that any code trying to do a copy is not going to compile because it's trying to access private things. But what about members or friends that tried to do copy assignment? What then?
We just don't define it so that linker tells us.
Okay. We won't get a compile time link because it's not a compiler problem if a member or friend tries to do an assignment. But if we don't define it at all, then the linker will tell us when we try to find the function, we declared it and never wrote it. Is that legal in C++ to declare a function and never write it?
Yes.
As long as you don't use it, declare away. Make promises. Sure. All right. So this is great. This was the best thing we could do in C++ or in classic C++, and it was even used by the standard. Okay, that's great. But we have a better option now, and that is to use deleted functions. So now we can say that copy assignment and copy construction, they're just equal delete. This is considered a declaration. We are declaring them, but we are declaring them to be deleted, meaning not legal. And if you do that, these make them also unmovable. And in fact, an easier way to do this is to just do one of the move operations equal delete, because the language definition says if you do the move is deleted, the other move will not be made and the copies will not be made. So this is a quick and easy way to say this object can't be moved, can't be deleted. Okay, everybody follow that? All right. So the guideline is explicitly disallow use of implicitly generated member functions that you don't want. And that's an update from Scott's advice. Well, it's actually the same item, but this is now saying use delete instead of making it private. Okay. All right. So now I have a question for you. Does C++ support self-modifying code?
Assembly code.
Okay, the answer is no, which is great. And the reason it's great is because C++ is hard enough for me to understand as it is. If those functions start changing themselves, I have no hope, right? But no, functions never modify. So what does it mean to have a const member function? What's const? All functions are const, right? They're just by nature, you never change a function. But in a const member function, what's really happening is, what are the real parameters to the function? If I have this, what are the real parameters? There's actually a this. Now, of course, let's understand this is not real code. This is what's really going on. And notice, this is what's really const. We don't have the const out here because the const is really this guy. Everybody understand that? All righty. So there's this implied this pointer, and that's what's const. Well, it turns out that they have taken, in the standard, they've taken the same concept and said that we can now do the same thing with references on member functions. We can declare a member function, and not only can we have const and non-const versions, but we can actually have L value and R value versions. So what is L value and R value here? It's the this parameter. Does that make sense? You understand? So what we're saying is that we can only call this function if the item that we're calling, remember it's a member function, so it's called on an object. Is the object we're calling it on an L value or an R value? If it's an L value, we call this one. If it's an R value, we call this one. Is everybody on board with that? Does that make sense? Okay. All right. Now, notice something, that if you assume that if we don't make it const, notice neither of these are const, if we assume that a non-const member function is non-const for a reason, that means it's modifying what? The object on which we're calling it. And if it's non-const and on an R value, what does that mean? We're modifying a temporary, right? Which is exactly what Scott didn't want us to do. So what that means is, now what I want to point out is there are times when we actually want to handle both of these cases. And I'm not talking about those. If you're already writing code that handles both of these cases, you want to handle the copy from case and the move from case, that's fine. What I'm about to tell you doesn't apply in that situation. If that's what you're doing, that's fine. And I actually call these ref qualified cases. But those are really rare. Most of the time, we don't need to worry about that. So I'm giving you the guideline for the non-ref qualified cases. That's where you're not trying to treat a special R value and L value versions, okay? So what I'm going to tell you is, so this is what Scott had said. We said we make them just return const, but we don't like that because we can't use move semantics. So that makes that not good. So instead, what we're going to do is we're going to combine deleted functions and the ref qualified functions, and we're going to say, look, in the case of assignment, either a copy assignment or a move assignment, let's not do the one where we're assigning to the temporary. Does that make sense? And in fact, it turns out that you don't actually even need to write this at all. because if you write this one, the compiler's not going to generate this one. If you don't write either, the compiler would generate one that would work in both cases. But if we specifically create the one that works in the L-value case, we don't actually have to do the R-value case one at all. Just do the L-value case by itself, and then the R-value case will not be written, and it will effectively be deleted, right? Okay. All right, so now here's the guideline, which is to return non-const objects to support move semantics, for ref implemented, those are the ones I said where you actually have something different you want to do in both cases. It's kind of rare, but we're going to call it out. But for other than that, for every non-static member function that is not a ref implemented, it should be qualified with either const or L value. If it's const, then that means it doesn't matter. You're not going to be modifying anything anyway. But if it's not const, then we only want to do it on the L value, because otherwise we're modifying an R value. Does that make sense? Okay. And again, this is not Scott's advice. This is my saying, this is an update of Scott's advice, because Scott didn't write this for modern C++. He wrote this for classic C++. So again, Howard said, you never want to modify a temporary except when you do. So we've been talking about move semantics, but there are other times when you may want to modify a temporary. Now, I don't think this is common, but one of the things, if you look at Scott's material, he's very honest with you. And even when he gives you advice, he'll call out and say, but there may be an exception to it. This is one of those times. So this is the advice, but there are actually times, and Scott didn't even talk about this, but not only for move semantics, but you may also have other situations. So here's an example. I'm calling a function that returns a string. So the return value from a function is a temporary, right? But in this case, I want to pass the result of that into a function that takes a string. Does that make sense? Call a function that gives me a string, pass it to a function that takes a string. But notice, I also want to trim it before I pass it. Something I might want to do. Does that make sense? But notice what I'm doing when I do the trim. If the trim is in place, if it's returning a trim, not an issue. But if the trim is done in place, then I'm modifying a temporary. Now, if we followed my new rule on Scott's idea, then that wouldn't compile, because you couldn't call trim on a temporary. So notice, you also wouldn't be able to do this if you'd follow Scott's original rule by making it const. So I don't think this is common, but I'm going to be honest, as I think Scott would be, and say there are times when this might be what you want to do. So this is my update for Scott's guideline, which is return non-const objects to support move semantics. If it's ref implemented, then go ahead and do the L value and the R value. That's fine. But for every non-static member function that is not ref implemented, should either be qualified with const or L value. That prevents the modification of temporaries. It doesn't inhibit move semantics, unless you really want to support modification of temporaries, which I think is not what we want to do. But in order to be clear, then you would not follow Scott's old advice or the new advice. That's a case where you say, okay, we're going to let you modify a temporary and let you possibly be doing something you don't want to do, because it's kind of rare that you'd want to do that. So anyway, that is my talk for tonight. Anybody have questions? No questions?
Do you have some more guidelines?
We went much faster. I did this same presentation in the Bay Area. The presentation you just saw took me an hour because I had so many questions. So you guys didn't ask enough questions, so it's all on you. I don't know what to tell you. I have 3 days worth of guidelines. I don't have any here to present. Any questions? Anybody want to talk about CPPCon? You can't shut me up if we start talking about CPPCon.
Yeah, you can invite everyone to CPPCon, I guess.
You're all invited. If you want to come to CPPCon, you need to go on the CPPCon website and go to registration and have us generate an invitation. And you want to get that done quickly, because there's a whole mess with immigration. You got to do that right away.
Yeah, I guess we have a question. Oh.
Yeah. Where's the question? Oh, back up there.
Can you comment how modern tools, compilers support these features. Maybe there are some specific in GCC or Microsoft compiler. What does it? How does it work?
I'm not sure I understand what you're asking. You mean
my question is, this is not theory only, but this is practice. Yes or not?
You mean will the compiler do the right thing if you write your code like that?
Yes. Does they understand these instructions correctly? So maybe implementation doesn't work correctly. No.
I'm sorry.
Is it fully supported by modern compilers or not? In various implementations, like Microsoft or GCC?
I'm not sure where they are. Each of the compilers has online pages that say which features are supported, and it is possible that ref implementations are not supported, but I suspect the recently shipping guidelines of all of those compilers are shipping with ref supported. I would be really surprised if that's not true. It's not that hard for them to implement that.
I've used this
You-
libraries, so the MSPC 2015 has a lot of bugs.
All right.
But GCC and Clang are both pretty good from...
All right, so Simon said modern, up-to-date versions of these are solid in both GCC and Clang. He says that it is implemented in Microsoft, but maybe a little buggy still.
Yeah, 2017 is okay.
2017 is solid, but 2015 is flaky. Does that help?
Yes, thank you.
All right.
Do you plan to publish another book? Just as a follow-up to Scored one.
I actually have thought about asking Scott if I could have permission to do an update on his books.
Just because Scott is not making any updates now.
Yes, and I suspect Scott might let me, but I also know that the standard, the bar is so high that it would be a lot of work to do that. And that's why Scott didn't want to do it himself. I mean, Scott understands if he were to release a 4th edition of Effective C++, that he would sell a lot of them. But it's a lot of work to do that for the new language, and so I think that's why he was put off. And if it scares Scott, then you better believe it scares me, right? But I have thought about it. I don't think it's going to happen. But I have given it some thought. Yeah. Yeah.
Do you write some blog with articles like this? Maybe periodically?
My blog, well, I showed you one of my blog posts. It was more of a rant. My blogs tend to be more rants about things than actually explaining things. I do these usually as talks, and every once in a while they'll appear online. Are you going to, you're recording this now, are you going to put this online? Yeah. So that's the kind of thing that I do.
Thank you.
Yeah.
Maybe do you have a YouTube channel with all these talks?
Yeah, actually, CPP Chat, if I do a talk like this, I'll put a link in the CPP Chat video. So,
Tell people what CPP Chat is actually.
so
I'm
CPP
not
Chat
sure
is
everyone aware.
my video blog, if you will. And how many of you listen to CPP Cast with Rob and Jason? All right. So theirs is, I think, quite professional. And mine is the opposite. So we have a joke. Whenever we have a technical problem, we say, we'll fix that in edit. And that's a joke because there's never an edit, because that would be time, and we don't spend any time. We just record it and upload it. Also, Rob and Jason are audio only. I have been video only. However, I'm working with Phil Nash, who's on the JetBrains team, to bring back, it's been kind of on hiatus for a while, so we're bringing it back. It's going to be both video and audio. And the reason that makes sense is because if you've watched any of Jens's videos, he does things like show you code and does great professional kinds. Well, I don't do any of that stuff. All I do is sit around and talk with people, and so there's no point in having video. So we are going to do an audio-only version so that people listen to it. But the point is, there is a channel, a YouTube channel, and I will, when I have other videos other than just that one, I'll push a link to those videos on that channel, or I'll push those videos up on the channel as well. So, so if you're interested in this kind of information, you'll see this every once in a while.
Since you started to talk about is const, I would like to know your opinion about trailing return types. At this point, so like, if you go east, you should go full east, I think.
So certainly, Phil, as I said, I'm working with Phil. Phil has written his own blog post, and he calls them east-end functions, where he's doing trailing return types, and he says, you know, it kind of makes sense to do this consistently. And he gives a couple of interesting reasons for that, and I'll let you read his blog. If you go to the address I showed you, //.info, that's my blog. And there's a page there for eastconst. It's in the menu, it's not just one of our, click the eastconst, and there's a list of links. And one of the links is to Phil Nash's blog post about east-end functions. And I can't really do justice to all the things he says, but one of the things he says is that it's consistent, because if you're using a return type for lambdas, although with C++ 14 we rarely need to do that, but if you're doing that, you have to use trailing return type. And in template code, we use trailing return type a lot, because we want to do deduction in a template deduction based on what the parameters are. And so we have to do trailing return type there. Again, in 14, not so much. But in 14, we still say auto. So to be consistent, if you always want to do it the same way, you're going to have to use east-end functions. The other thing he points out is that a lot of other languages are doing this. And so Phil has been working with other languages, and he sees, particularly in functional languages, they use trailing return types. That's just the only way they do it in that particular function. And then the other thing he points out is that when declaring a function, usually the most important thing about the function is the name of the function. Then the next most important things are the parameters. And the return type, less important. So he says it just kind of makes sense that you put the return type at the end. So I don't know if I did justice to Phil's arguments. I think you should read his blog post. But I have found that I tend to do return types a lot. I'm not sure I do it 100% consistent, but I'm sympathetic to his point of view.
In the beginning of your lecture, you said about revolution in C++, east-west const, and what do you think about changes in C++ in next few years? For example, maybe sometimes we refuse from raw pointers and we'll use just references and smart pointers. How do you think about it?
Are you saying should we get rid of raw pointers out of the language? Is it still the 1st of April? I don't know what's going on here. I think part of the reason that April Fool, for those of you who don't know, there's an April Fool's joke that several bloggers published on the 1st of April saying that there's proposals to remove raw pointers from the language. And part of the reason that makes so much sense is because raw pointers, although in practice they're absolutely critical for doing many low-level libraries, they in fact are not practical to use. Even in many libraries, you wouldn't want to use a raw pointer. And certainly as an application programmer, raw pointers are probably a smell. Right? But we're not going to get rid of them in the language. One of the interesting things about C++ is that it's kind of like new and delete. Right? We're now encouraging an application program, don't use new and delete. We're not going to take them out of the language because somebody has to use new and delete. We've got to do that somewhere, and there has to be code to do that. So we already are kind of in a situation where there's certain things that are pretty much, application programmers shouldn't do that. And it's not because of who they are, it's because of what they're doing. If you really want to do new and delete, that probably should be wrapped in an object handled by a library at a lower level. And I think with raw pointers, that's pretty much the way it is. That we probably don't want, in most regular application code, we don't want to use raw pointers. We use raw pointers internal to data structures that are kind of low level and well baked. And that makes sense. But in applications, probably not as much. Are we keeping people from pizza? I don't want to be, I don't
no.
want to stand between a programmer and
No,
pizza.
there is some delay, so they're still delivering it. So if you have more questions, we can proceed.
Okay. Does everybody know what a software engineer is? Does everybody know what a software engineer is? A software engineer is a device for turning caffeine and carbohydrates into algorithms, right? So everybody knew that, right? Okay. I was teaching a class in India, and they had delivered all these cookies, and the class was being very well behaved and polite, and they were all sitting there. This was at break time, and they were all sitting there, and I said, I don't believe you're real software engineers, and I think they were offended and shocked that I would say that. I said, well, you know, a real software engineer would be eating the cookies. They're free cookies, you know. Real software engineers eat cookies, right?
I'm going to give a very short talk about C++ and how it's a reasonable programming language for reasonable people to use. And this is me, I'm Simon Brown. You can find me at Twitter, I'm at Tartan Llama. So in C++, you can introduce undefined behaviors to your program by changing where you write equals default. In this first one here, we write it on the declaration. This is exactly the same, but we write on the definition. There we go, turned on. So here we write default on the declaration, here it's on the definition. Reading A.A is okay, and B.B is undefined behavior, because C++, next. Okay, in C++, this is valid code. We can have a class called A, and a virtual member function called foo, and then we can derive from it and just write b a foo. As many times as you want, you can write this. Your entire slide, this entire page could just be B's, and it works. C++. In C++, you get a cache miss on pretty much every lookup in std unordered map. I don't have any code for this. It just makes me mad. C++. In C++, you can store state at compile time by defining friend functions. So what we do is we have some function which we declare. We then have a template function which defines this member function only when it's instantiated. We place this instantiation into a context which we control, and then we can just have context per invocations of this function which return different things. Don't expect to understand this. C++. In C++, some types are foot guns. We have std variant in C++ 17. It's great, mostly. We have a variant of string and bool, and we initialize it with oh no. And of course, this initializes the bool, because this is this will decay to a pointer, and the pointer is not null, so it's true, and this will actually just print out 1. C++. In C++, non-allocating strings are also foot guns. We have a std string, and we append something to it. This is getting back to our temporaries. And we store it in a string view, and this temporary will all die and go away, and now we have a dangling reference. C++. This is me writing C++. In C++, my std expected assignment operator, I implemented std expected, is hundreds of lines of template nonsense. I mean, you might think, like, surely it can't be hundreds of lines just for the assignment operator. But this is some of it, and this is some more, and maybe you get the idea. C++ is great. Even more. Implicit conversions. C++. C++ is a reasonable language for reasonable people. Thank you. Any questions? Yes. Pardon? What's your point? My point is C++ can be ridiculous, and it's quite fun to talk about how ridiculous it is. Any other questions? No, okay, thank you.